There are a few standard enclosure problems that you should know, and we'll discuss them in this section. The simple three-sided enclosure, which can either be a triangular channel or a cylinder, where the top has some temperature T1, the sides have some temperature T3, and the base has a temperature T2. This problem is perfectly suited for a circuit analogy. We understand that there's a surface resistance for surface 1, 1 minus epsilon 1 over epsilon 1 A1. Similar resistances for surfaces 2 and surface 3. We understand that the geometric resistances are specified in terms of the view factors. These view factors are identified and are known from tables and charts. And this is just a very simple system of equations. If the temperatures are known on these different sides, then the questions that might be asked are, what are the heat fluxes or the heat transfer rates on the different surfaces? And so solving this problem, again, is just in terms of identifying what the J equations look like. And once we identify those J equations, we are able to race through this problem. And an example of this will be shown. Another simple three-sided enclosure is shown here. The difference is that this has an insulated third wall. So unlike the previous example where the third wall had a heat transfer rate through it, this case it doesn't. And there's an interesting simplification that occurs for that problem. In both cases, we have this three-sided circuit system. The difference is that the heat transfer rate through side 3 is equal to 0. If you think about that, if Q is equal to 0 is equal to EB3 minus J3 over the surface resistance of 3, it means, multiplying through by RS3, that EB3 is equal to J3. So the radiosity and the blackbody emissive powers for surface 3 are the same. Because there's no heat transfer that passes through node J3, another simplification is available, and that's that there is no path to a different potential from J3. Essentially, this problem now has been simplified to look like the following. So I'm just going to sketch it just a little bit differently from what we had there. We're going to make it more explicit. So this is our J3, but that node is not very important. We have our R geometric here, another R geometric here. And so what it says is that between 1 and 2, there are two paths. It's a parallel circuit, and we use a parallel circuit model to define that. So this can be further simplified. In terms of equivalent series resistances. So we can combine the RG, you might call it 1, 3, and 2, 3 here, into a R effective or R total on that path. So this is the path from 1 to 2. the indirect path from 1 to 2, we might call 1, 3, 2, as compared to the direct path from 1 to 2, which is shown above. And so the two surface resistances, RS1 and RS2, are still evident here. And the total resistance associated with this parallel section is provided in this this piece here, in this middle piece here. So this is a standard type of problem, and that you should be familiar with, and you should be able to derive these results and use them. Given what we show up here, it's relatively easy to find Q1 and Q2. We might also want to calculate T3. To find T3 means that we need to know JR, what we're calling R is this so-called re-radiating surface radiosity. So an adiabatic surface in radiation is called a re-radiating surface. And so this is the re-radiating surface radiosity. Hence the subscript R. R is for re-radiating. So to find, remember we said that J re-radiating is EB for the re-radiating surface also. So once we know the re-radiating surface radiosity, we know its temperature, because this is just T to the fourth here, sigma T to the fourth. The way that we find this is if all of our radiosities, if our main radiosities are J1 and J2 are known, I hope that you see that once we find Q, so if we find Q, which is the overall potential drop in this system, then we know what the intermediate J's are, because we can go from EB1 to J1 and EB2 to J2. So once we know our Q through the whole system, that has to be the same Q that goes through RS1 and the same Q that goes through RS2. That immediately tells us what our J1 and J2 will be. Once we know our J1 and J2, we can then think about the off path, which is the path through the re-radiating surface. So if we know J1, JR, J2, the current flow, if you will, from J1 to JR is the same as from JR to J2, which is what we're setting up here as the total energy balance or power balance on surface JR of that node. We can solve for JR, and once we know JR, of course, we know what E of the re-radiant surface, the blackbody emissive power of the re-radiant surface is, and we know what the temperature is. As we said before, since Q3 is equal to 0, we get the result for JR. The temperature is simply JR divided by the Stefan-Boltzmann constant. Raised to the 1/4 power. And an important issue is that this temperature is independent of the emissivity of that surface. So we can prescribe an emissivity for the re-radiating surface, but its actual temperature doesn't depend on it. The last relatively simple case is a radiation shield. So if we have a simple two-sided enclosure, so the two-sided enclosure problem is two large parallel plates. I'm drawing this a little bit differently from what we have here. So epsilon 1, T1, epsilon 2, T2. For that case, the heat transfer rate between surfaces 1 and 2, you can think about it as Q1, 2, it's Q1 or minus Q2. Sign matters only in terms of which orientation or which direction you you just prescribe it as. And so we know that this is the change in emissive power, blackbody emissive power, divided by the resistances, surface resistance 1, the geometric resistance. I hope you see that there is a geometric resistance even for flat plates that see each other completely. And the way to think about that, of course, is that certainly F12 is equal to 1, but even having F12 is equal to 1 doesn't mean that I get rid of that geometric resistance. So I don't get rid of the geometric resistance because the surfaces see each other completely. It's just that I have that factor of 1 over the area in there, basically. Oftentimes, though, and you might think about a Dewar or other systems, you might want to have a very highly reflective radiation shield between these two surfaces. If I can't assure myself that I can get low emissivities for these surfaces or high reflectivities, what I might do is put this intermediate layer in there where I might choose the emissivities appropriately. And so in specifying a problem of that type, what we have then is we have a problem where, and this is condensed, but where we might think about it sort of in the more fully fleshed out version as having geometric resistances on our primary surfaces, view factor to our primary surface. I'm going to say this is 1 over 1. I hope you recognize why it might be confusing. So let's just do this. The areas are all the same. So we have A here. F1 to the shield is 1. Geometric resistance on one side of the shield, epsilon shield side 1 divided by epsilon shield side 1 times the area. Shield side 2 geometric resistance, view factor between the shield and surface 2, and finally geometric resistance on surface 2. So this is the sort of the full, and then of course here's our delta EB in the numerator. So here's our gory, fully fleshed out version. Areas are put up in the denominator. So this is 1 over epsilon 1 minus 1 plus 1, 1 minus epsilon 2 over epsilon 2, which is 1 over epsilon 2 minus 1 plus 1. And so what you see is that what we end up getting is we just get 1 over epsilon 1 plus 1 over epsilon 2, and then the shield properties here. And so this is, again, a very straightforward calculation. It's important for you to understand how this was developed, and so that you can apply it in both quizzes and in exams.